Good morning, welcome to my kitchen. So I'm hoping you'll have all these ingredients ready to have a little go at this experiment. We'll see how it goes. Small one is in the other room looking at the iPad, so hopefully she won't interrupt, but it'll be funny if she does, I suppose. So what you need is some sort of clear container or glass, sort of a third full of water, and then if you can, a similar sized or an equal sized glass of some thick sort of viscous liquid, something like honey or syrup or treacle or something like that you've got sat in the cupboards at home. You will need 1 or 2 drinking straws, eco-friendly straws preferably, and then you'll need some sort of fizzy bottled drink that hasn't been opened yet. This is, I think, tonic water or elderflower something or other. So that's all you need. You set the label off so that you can see the liquid inside all become clear. So we're talking about volcanic eruptions and sort of about how they work. So the first little bit before you do this that I'll set on the classroom is you have a little look at how would you describe a volcanic eruption, and this all kind of feeds into that explanation. So hopefully you said something like explosive, some sort of big catastrophic event, something like that. But we want to know actually why the eruption happens in the first place and what types of different eruptions we have. So this experiment will kind of help us with that. So first thing we need to do is grab your water, and I'm going to put on the classroom like a little worksheet that you can kind of go through and add your observations. If you're not actually doing the experiment at home, then obviously use this, and I'll try and get this as close as I can to the camera so you can use this instead as your sort of observations. So all you're going to do is shove your drinking straw in the bottom and just blow steadily into the water until you get some bubbles. It's really important with this one that you try and kind of remember at what pressure you are blowing into the water, because we're going to compare it in a second to the honey. So I'll do it as close to the screen as I can so that you can see at home. So hopefully you can see there was quite rapid movement of bubbles. They very quickly got to the surface. In terms of size, they were quite big. And notice now the liquid is now completely clear of bubbles. All the bubbles have surfaced to the top and popped. So that's our first observation for our nice, very runny, fluidy water. So now if we do the same with the honey, again, on your sheet, note down what you see. So I'm going to try and blow a similar pressure. I might not be able to, in which case I might have to up it, but we'll see how it goes. So to get the initial bubble, I actually had to put quite a bit more pressure in to blowing. So in comparison, this one took a lot more energy to try and get some sort of bubbles to come to the surface. I'll do it again, and what I might try and do is, if I can, hold both to the camera and blow both at the same time. So in fact, if I do the same pressure, I actually only get bubbles in the liquidy one. And again, you'd expect that because it's a much thicker, stickier liquid. So again, notice how the bubbles actually move. And look at the size of the bubbles too. I'll just do a really high pressured one, and I'll explain why in a second. So if you blow really, really fast, you get some really, really big bubbles coming to the surface, and they actually come quite far up the glass too. So you notice the bubble almost filled the entire glass. What you'll notice as well, if you look really carefully now, up to the camera, a lot of those bubbles are still stuck in that liquid as well. So not all of them have actually risen to the surface. The gases are still kind of contained within this really thick, viscous liquid. So there are definitely some differences. And I guess what I want you to guess first of all is between the two, which one do you think is going to give you a really big explosive eruption? Now, a lot of people guess the water because actually when you put a lot of pressure into the water, bits of water kind of spray everywhere. That doesn't happen with this. But actually, if you compare the size of the bubbles and how far the bubbles actually travel up the glass, hopefully you'll realise that this thick, viscous one has a really, really big build-up of pressure and a very sudden release of pressure. So it's this thick, viscous one that is going to give us a really big, explosive eruption. So it tells us something about what sort of volcanoes give us big eruptions and what the magma is going to be like in those volcanoes to create those eruptions. So where we have normally very small, very unactive, very undangerous volcanic eruptions, we tend to have really, really thin, runny lavas. So if you go to Hawaii, you can go up to some of the tops of the volcanoes, you can actually go and play with the lava. It's really quite thin and runny, and it will just flow across the landscape. It doesn't really endanger anybody because it's not explosive, it's not big, there's no danger when you get there. And that runny lava just kind of works its way over the landscape and doesn't really do an awful lot. The volcano you wouldn't want to be around when it erupts is one that has a really thick, viscous lava, because that lava is not just going to nicely, slowly come out like it would with a Hawaiian volcano. It's going to very suddenly explode out when it's got enough pressure behind it. It took me a lot to build up the pressure in this liquid to actually get an eruption, if you like. So it needs a big build-up of pressure. And of course, a big build-up of pressure with a lot of thick magma is going to give us a very, very big explosive eruption. So yeah, never go to a volcano that's got a thick, viscous magma or you're kind of in trouble. And as you can see, the gas is kind of trapped in the thick, viscous lava too, which again will build up a certain amount of pressure. The last one that we'll do before we then kind of explain everything all put together is our one with our bottle of carbonated water or lemonade or whatever it is. So if you've got one at home, grab your bottle. It's also in the fridge, it's all condensation-y now. And make sure the label's off so you can actually see the liquid inside, because that's quite important. Again, there's a little bit on your observation sheet to fill in for this one too. So first of all, when you get the bottle, give it a squeeze. You'll notice it's quite difficult to squeeze. It's pressurised and it's carbonated, so it's going to be difficult. But you can kind of just about depress it a little bit, and we're hoping for a change after this. So just kind of note mentally what it feels like when you squeeze that bottle. And we're going to do a couple of things. So first of all, I just want you to very lightly shake the bottle and then have a look at what you get inside in terms of the bubbles. And again, I'll hold this up to the camera so you can see if you're not doing this at home. So just a quick kind of turnover and then have a little look. I don't know if you can see that, it's clear enough, but I'll do it again. We've got some bubbles, they fairly quickly rise to the top. If you have a look at the top, put it a bit further away, they sort of pop in at the top up here and sort of disappearing, and I've still got a few small bubbles kind of just working their way to the top even a little while after. And then if you have a little squeeze of your bottle, you can still kind of squish it pretty much like you could before. All you've done by shaking it is you've created a bit of a reaction, and that reaction has released carbon dioxide, which is the little bubbles that you then see. And obviously some of the air at the top, when you shake it upside down, gets caught up in there too. So you've kind of got two things going on. This air kind of gets trapped in the liquid and tries to resurface, and you've also got a chemical reaction making some carbon dioxide, which is then slowly coming to the top too. Now what I'd like you to do is, and again, we want to see some sort of comparison, is shake the bottle vigorously for sort of 15-20 seconds or so. It says on your sheet 30, but it doesn't make any difference after about 10 or 15 anyway. And then note down what you see. So I'll give it a good shake. Well, the heart's going to kill me, so this is tonic water. You'll notice as you're doing it, if you're having a look at the bottle, it almost goes white because there's so much gas now in that liquid. And again, if I hold it up to the camera quite quickly, you should see a whole snowstorm of bubbles. And it takes much longer for those bubbles to surface to the top. There's still bubbles, there's still little bubbles, and there'll be some for some time afterwards. Again, if I kind of replicate it again and just show you the top of the bottle, you'll see what's going on there. So again, in comparison, we've got a lot more happening at the top of the bottle. There's a lot of foam, a lot of bubbles rising to the top and then popping. So again, what you've done is on a larger scale, you've created a reaction. I've still got tons of bubbles sort of sat on the side of the bottle still still rising to the top. And that reaction has caused lots of the carbon within the liquid to turn into its gas form, and those bubbles have risen to the top, and they're starting to occupy this space at the top of the bottle. If you now try and depress your bottle, mine is noticeably firmer, and the more you do this, the more you'll pressurise the bottle. We know it's pressurised because you know exactly what would happen if I took the lid off right now. We'd release that pressure, it'd probably go everywhere. I'll let you do that at home if you want to. I'm not going to make a mess of my kitchen. But yes, we've just pressurised that bottle, and we've added more of the carbon dioxide that was contained in the liquid to the top of that bottle. Why does that matter? Well, the same thing happens in a volcano, and quite luckily, this bottle maybe not quite so much, but you know there's other bottled waters you get that are almost kind of volcano shaped. They kind of mimic what's going on. So if you think about the inside of a volcano, you've kind of got the bung on the top, the bit of solid rock that's keeping everything in. You've got what's called the conduit, which is kind of like the neck, or the tube that takes the magma from the bottom up to the vent at the top. Which again, if you've got one of those other sort of better bottles that are more like that shape, you can kind of see. And then underneath you've got this big bulbous magma chamber that contains all of the magma inside it before it eventually erupts. And what you would get in a volcano is exactly the same. You would have this bung on the top of rock that's keeping everything pressurised inside. Underneath you will have kind of a void in the conduit, which is kind of the pipe that takes the magma up, which would basically be filled with air for a certain amount of time until an eruption happens. And underneath, obviously here we've got liquid, would be our magma. So we have the same thing. And we also have chemical reactions going on within magma. It's not just a nice benign liquid that nothing happens in. We get chemical reactions, and gases are produced in those chemical reactions. If you've ever been to anywhere near a volcano, they say be very, very careful. So if it's near an eruption, it will start emitting gases, and that's where the gases from the top pressurised bit are slowly kind of leaking out. They're very toxic, can be very harmful, and then can actually give you nasty sort of lung diseases. Sorry, off topic a little bit. But yeah, we have exactly the same components in the bottle that we have in the volcano, maybe just a little bit hotter. So imagine this is your magma, imagine this is the air in the conduit, and imagine this is your kind of plug of your vent at the top. We're doing exactly the same. So the chemical reactions that will be happening in the magma will be pressurising the air at the top, and at some point that pressure from the air and the gas bubbles and the build-up of magma underneath will become such a force and such a high pressure that it will force our top off. Now, luckily, because these are pressurised bottles, I can shake this as much as I want, and I'm never ever going to get this cap to suddenly come off unless I use some fancy shaking machine. I obviously have to twist it to do so. But you can with, if you've ever done like a champagne bottle or something, got the cork a little bit to the top and then shaking it, it can be enough pressure to then force the cork off, and the cork goes flying, doesn't it? So you can sort of mimic it with a bottle of champagne. Sorry, it's a budget video. But yeah, you know exactly what would happen if we depressurised this. Now, the more pressure and the more gas we add to this, the more explosive that reaction is going to be when I take this top off. That's exactly the same. So the more pressure we can create inside the magma chamber of a volcano, the more of a reaction we're going to get. And as we saw with our two liquids, which one stored the most gas? It was our honey. In fact, if you have a little look, there are still tiny little bubbles contained within the honey. So we know that a thick, viscous lava is going to create a more pressurised environment. So if we mix these two things together, we're going to get the ultimate explosive volcano. A thick, viscous lava inside of here, a massive buildup of gas would create a massive kind of pressure on our vent, and would get a really, really big reaction. In contrast, if we had a really runny, liquidy lava and we didn't have much gas, we wouldn't get much pressure, and therefore at some point it would just slowly break through the top, and we'd probably get some nice trickles of magma down the side like we do in places like Hawaii. So that's our little experiment. Obviously, if you want to at home, you can take and depressurise your bottle if you just want a bit of fun. And if you did manage to get hold of a little bottle of Coke or something and a Mento, again, you can recreate what happens when you then sort of up that chemical reaction. So what you're doing by putting the Mentos into the bottle is creating a chemical reaction, which the byproduct of is a big gas. Again, it pressurises your bottle. Please don't put the top on because I've tried it before and it explodes everywhere. That's the one where you can depressurize a bottle, trust me. And it makes a really loud noise too. I once did it in an A-level class, never doing it again. But yeah, again, you'll get a nice big eruption. Do it over a tray or something where your parents are going to kill me. But that is it. That is how we can kind of attempt to mimic a volcanic eruption with a bottle and some honey. So we're going to go on to some other stuff. I'll stop the video and I'll put some instructions on Classroom because that's I think about all I need to say to you guys for today. There's a little game to play later on as well about guess the VEI. And I think we'll kind of just about get to the ends of types of eruptions today. So I'll refer back to Classroom, instructions will be there. See you later.